What is up everyone, and welcome to the first tutorial in our TensorFlow series. My name guiding you through this tutorial as well as through the next few TensorFlow tutorials in which we'll build a few projects together, and we'll also show you how to add TensorFlow to Android Studio. Now at this point, and actually before we go any further, I'm going to assume that you know at least a little bit about Python programming. As well, we're going to be working in PyCharm just because I think this is a nice IDE and makes building and running our Python programs easy. So if you have no experience programming in Python or using PyCharm, I suggest you watch our tutorial series on the intro to Python in PyCharm. I also did that one and should be included in the Hello Coding package anyway. But assuming you're comfortable enough with that stuff, let's learn about TensorFlow itself. So in this tutorial, we're just going to be covering the basics of the TensorFlow components and roughly how to build a small program and use TensorFlow in PyCharm. So we'll start just by learning about each of the components of building up a TensorFlow project, including building up the computational graph and then training your program. And finally, we'll cover how to test your program by building a small program ourselves, which will basically simulate a simple linear regression type model. Now keep in mind as we go through this tutorial that this is just going to be an intro into the very basics of TensorFlow. And as we work through the other projects, we're going to see a variety of different libraries that are going to be used and a bunch of different machine learning techniques. However, this is a good place to start if you have no machine learning experience, particularly if you've never used TensorFlow before. So without further ado, let's get started. I just started up an instance of PyCharm. Okay, keep in mind this is version 2017.2.3, and I'm going to be using Python 3.6. So make sure you've got all of the latest stuff because this will help with the imports. If you don't have the latest version of PyCharm or the latest version of Python, you might not have access to some of the libraries we're going to be using. So we're just going to start by creating a new project. Let's just call this something like TensorFlow Basics or Intro. You can actually, instead of doing this, click right on this item. Choose a location. You can go just like the desktop or something. That's fine. I'm going to go ahead and open that up. But make sure you're going to be saving this in a folder you'll be able to easily access and probably won't be moving around too much. As you can see, the interpreter is going to be using 3.6.2. And keep in mind, if you use a different version of Python, you might not have access to some of the same frameworks and libraries that we'll be using. So we'll go ahead and create that project. And don't worry about this, we'll just go ahead and select no, and this will just create our new project for us. So it's just going to take a little while to set up, just needs to scan some files to index. And then once that's done, we'll start just with a basic intro into first what TensorFlow is and what it's going to do for us. This is just going to be basically a text file that I've written that will just provide a brief intro into kind of the topics we're going to be covering, as well as give an overview as to how TensorFlow works and some of the components of it. Once we're done with the intro, we'll explore some specific components, then we'll talk a little bit about linear regression, then build up our linear regression model, and then we'll be done and ready to start some of our real projects. So as always, if you're finding these tutorials a little slow, then feel free to watch these at kind of 1.5 or 2 times speed, but don't skip over entire sections as we're going to be covering some pretty complex stuff, and TensorFlow can be a little confusing for those who have never used it before. So why don't we go ahead and get started with our brief talk into the overview of TensorFlow and roughly how we're going to be using it in our projects. Alright guys, having started our new PyCharm project and having gone over our learning goals, we can now launch into a quick discussion about exactly what TensorFlow is and how we might use it in our projects. Now this section is just designed as a brief overview of TensorFlow as a whole, not about the finer inner workings of it. And it's just going to be basically a bunch of me talking and going over these points I've outlined here. So if you already understand the basics of TensorFlow, feel free to skip this section. But if you've never used TensorFlow before or you're a little unsure of how it works, I do encourage you to watch this. Now, that being said, you can watch it a little faster if you want. As like I said, it's just going to be basically a bunch of me talking and going over these points rather than writing any actual code. So let's go ahead and get started by talking exactly about what a TensorFlow is. So TensorFlow is essentially a massive library that is used to incorporate machine learning into our projects. Now, when I say that it's a massive library, I mean that essentially it provides a bunch of high-level APIs and data. So not only does it contain a bunch of variables, functions, and classes that will help us to build stuff like computational graphs and run our actual models, but it provides a bunch of already built-in datasets or gives us easy access to those datasets. Now, one of the great things about TensorFlow is that it can be incorporated into a large number of platforms. So we're just using it with Python and PyCharm right now, but we can also incorporate it into stuff like mobile projects by importing it into Android Studio, for example, or using it in web applications with JavaScript. And unlike a lot of already included machine learning libraries and platforms, it allows us to not only build and run our model, but also to train the data ourselves. At the same time, these high-level APIs provide us a bunch of different, again, classes and functions that do a lot of the behind the scenes work for us. All we really need to do is build up our model and then go ahead and run it. That being said, there's a few steps to this process which we'll explore in just a couple of minutes here. So first, TensorFlow is built around the idea of tensors. Now tensors, or tensors, I don't know how you want to pronounce them, are our basic units of data within TensorFlow. So these we can essentially think of as being arrays of primitive values, so arrays of strings, arrays of numbers, and so on and so forth. This is how we're going to input our data into the model. Now that means that any kind of data we're putting in, be it images or audio or text or something like this all needs to be converted into tensors or into arrays. This is easy enough if we're just working with simple numerical models, but for example, stuff like a text prediction model might take in an array of text, and we would have to divide that array of text into smaller arrays of the individual strings that might represent single words. Similarly, if we're feeding in stuff like image data, well, then we need to convert that image data into basically these arrays of maybe pixel values or RGBA values or something like this. Either way, the data we feed in needs to be in a tensor format, and this can be a lot of the challenge, is trying to find a clever way to convert your data into a type into which we can feed, or rather, that we can feed into our model. Now, as I just mentioned, building a program in TensorFlow can be divided into two main sections or two main tasks. The first is going to be building up our computational graph using nodes and a bunch of variables and values. And the second part is going to be running our graph, be it to train the model, to assess the validity or accuracy of the model, or to actually compute and predict something. So, building the graph or the computational model itself is, in my opinion, actually the hardest part about this. And the reason it's so difficult is that it's a pretty finicky process. There's a lot of different parameters to take into consideration, and finding the optimal model to use as prediction can be a bit of an art in and of itself. This is unfortunately just something that comes with practice and experience using TensorFlow. And the most optimal model is very often not clear right off the bat. However, all I can do is teach you the basics, provide you a few examples, and then it's up to you guys to try to find the optimal solution to these problems. But the first step to building our computational model or our computational graph, and actually, by the way, as an aside, when I say graph, I don't mean kind of like an X and Y axis kind of graph. I mean a graph that's built based on interconnected nodes. So if you're not sure what that is, then search up something like computer science graph, and you'll get the general idea from there. So as I was saying, our computational model is built entirely around a graph of nodes. So each of these nodes is going to take 0 or more tensors or arrays as input. So again, the first step is always going to be to convert our data that we're feeding in into some kind of a tensor form. Then we'll need to use various types of nodes to build up our computational model. As well, we'll need to specify parameters such as the model type that we want to use. I think to keep things simple, and because it's one of the simplest models anyway, we're going to start off with linear regression, but we won't explore that in greater detail until a few sections from now. We'll also want to specify stuff like a series of input parameters or input values, and then the expected output that we'd get that would correspond with these. So for example, let's say we were building kind of like an image recognition model. Maybe we'll want to feed in some images of like a boat, a cat, and a rabbit or something, and then the expected outputs would be the words that would represent those. So the inputs would be the images themselves, obviously converted into a tensor form, and then the output would be the words that would represent those images. As well, we'll need to specify which parameters we want to optimize within our model. So for example, with a simple linear regression model, which is basically y equals mx plus b, the input values would be our x values, the output values would be the y values, and the parameters we want our model to optimize would be our m, or our slope, and b, which is our y-intercept. And then after this, once we've built our model as basically a graph of nodes, we'll probably want some kind of data to train our model, as well as some data to test our model. Now, generally speaking, we want to divide our total data set into about an 80-20 split, and I mean 80%, 20%. So 80% is going to be training data, and 20% is going to be the testing data. Now, the difference between the two is that the training data is obviously, as its name might imply, going to be used to train our model. So for example, we'd feed in some images of, again, like a boat, a cat, and a rabbit, and we want to train our model in such a way that it will output those values. Then we'll of course want some testing data which is different from our training data, and this is going to be used to assess how accurate our model is. So if at the end of the day our model is very inaccurate, we might want to either adjust the model parameters or feed in some more data and train it further. So as you can see, there's a lot that goes into building this model, and there's a lot that can change about it, which is why building this model can be so difficult sometimes. You want a model that's not just accurate, but also efficient as well. I mean, if your model takes ages and ages, days, weeks, maybe even months to process some data and give you a result, probably not the best model. And you'll probably want to either adjust the data you fed into it, or you'll want to adjust some of the parameters. As well, finding stuff like how to start our model, as in the beginning values that we put in, can be a challenge as well, as typically we'll provide some initial values for these parameters and then allow our model to adjust these values to find the optimal solution. However, it's kind of difficult to understand how much of a challenge this can be without seeing the actual model right in front of us as a quick example. So we'll save a further discussion for this when it comes time to actually start building up our simple linear regression model. So that's the basics of building up our model. So once we have the model built, the second step will be to obviously run our model. Now we'll want to do this in a few different stages. And the first stage will be to train our model. So once we've trained it, we'll run it on some testing data. And then once we've done that and we're happy with the results, we think our model is accurate enough, then we can go to input some real data and go about using our model in the real world. So basically, once a graph is built, we run what's called a session on our graph, and that will output any expected results. So how accurate the model is, what the expected values are, and so on and so forth. Now, when we run it, obviously we'll need some kind of input values to start off with, and some kind of expected outputs. Now, this is mostly used in our training data, whereas when we're going to test it, we'd simply just put in the inputs, and then it would give us some outputs, and we assess the validity or accuracy of those results. As well, we'll want to specify how many epochs we want to run our model on, which is essentially how many times we want our model to run. And also, we'll want to specify stuff like the learning rate, which is kind of how values are going to change over time and how quickly they will change. Again, this is a bit of an art in and of itself, because if we run the model too many times, it's just going to take too long to calculate the data. But if we don't run it enough times, then we're probably not going to get accurate results. This is similar to trying to find the optimal learning rate, because if we learn too slowly, it's going to take ages and ages to run. But again, if we learn too quickly, then we might get a slightly less accurate model. So, although it's not difficult to use, TensorFlow actually makes things really easy, again by providing these high-level APIs. The challenge comes in finding the most efficient way to go about using it to solve your problems. As well, finding enough data for our training and testing datasets can be a bit of a problem, particularly if you're using stuff like images. Luckily, there are massive libraries out there, some of which we gain access to thanks to TensorFlow, and huge datasets that already allow us access to a bunch of already trained data. Or if we're building something completely new and novel, then we'll have to train the data ourselves. So although building the model can be the toughest part, training the model, depending on how much data you're using, can be the most time-consuming part. But I'm not giving you all these warnings to kind of scare you away from this. Quite the opposite. I hope to intrigue you guys and get you guys thinking about how you might go about building your models, how you might go about training them, and keeping all of these ideas in mind as we go to build our models to hopefully solve some interesting problems. And speaking of the models, I'm actually at this point going to assume that you know at least some of the basics about some of the simple machine learning models that we might use. Now, we're going to cover mostly linear regression. We may move into some of the other ones depending on how much time we have. But if you're completely unsure, know nothing about machine learning, and want to know a bit more about some of the mechanisms behind some of these machine learning models, I do recommend that you go and search for yourself, as these tutorials are more about how to use TensorFlow and incorporate it into your programs than about machine learning as a whole. Now, that being said, I will explain a bit more about linear regression in a few sections when it comes time to actually build our simple linear regression model. For now, just think about it as being basically a way to estimate a line that fits some data, okay, and then we're going to run our model to basically optimize this fit. So essentially what this will do is, again, like I said, linear regression is just using our basic equation for a line, y equals mx plus b, and then trying to find the optimal values for the slope and the intercept. And this will help us to determine a line that best fits some data. So that's really what it does. It basically, we feed in the inputs and the expected outputs, and it trains this line to kind of move around until it finds that model that minimizes the differences between the expectations and what's actually being outputted. But like I said, more on this a little later. In a few sections, once we cover the very basics of how to build up our model, we'll actually build a model from scratch ourselves. But before we can do that, we need to learn the code portion of how to build our computational model, and we'll get started by learning just about some nodes. So that's what's going to be coming up in this section. We'll just cover the basics of some of the nodes we might use, and then in either the next section or the one after that, we'll talk about how to actually run our model to output the results found from building this computational graph. So hopefully by this point you understand a little bit more about exactly what you're going to be working with. And if you're happy and ready to move on, let's start writing some actual code and starting to build up our computational graph. Hi guys, at this point I'll assume you know at least a little bit about how TensorFlow works, either from having watched our overview section, which we did previously, or from just having some general knowledge of TensorFlow to begin with. Either way, we're going to start learning how to create our computational graph, which will be essentially designing the model for our particular program. Now, before we go about building the graph itself, we need to learn about all of its components and how they work together. The simplest components of the graph are going to be our nodes. So we're going to explore all the different kinds of nodes that we'll be using to build our linear regression model, starting in this section with our constant and our operator nodes. Now, these are two of the more simple types, and either hold a value or values, or the results of some kind of an operation. So we'll first take a look at how to set up and use these particular nodes, and then we'll take a look at how to run the nodes to output their values using some TensorFlow sessions. As the tutorial progresses and we move on to the next few sections, we can explore some different kinds of nodes, and then finally, once we're comfortable with all of the nodes we'll be using in our linear regression model, we can work to actually build up that model from the start. So let's work on our constant and operator nodes, and before we can do anything else with TensorFlow, we have to import the TensorFlow library. So this is done with a simple import statement. By the way, I just started a new file here. I call this one node types part 1, and it just exists within my main directory right next to my notes here. So I think we can actually go ahead and close that project up and continue on with our import statement. So we want to import TensorFlow. Okay, and I'm going to import this as TF so I can use my shorthand. Now, unless you've already imported and installed TensorFlow before, this will likely give you a red squiggly line saying that you need to install the package. So assuming that you are using the latest version of PyCharm and the latest version of Python, and know a little bit about Python programming either from previous experience or having watched our Intro to Python tutorial, then you should actually have access to this TensorFlow package. So you just need to go ahead and install it. You can click on the TensorFlow word itself, hold down Option, press Enter or Return, and you should have as one of these options the ability to install TensorFlow or to import the package. Now, once you install it once, it should be available for all your projects, hence why I do not get an error. So I'm going to assume that from this point on, you have successfully installed TensorFlow and have access to all of its libraries. So just take a moment to go ahead and do that. It should only take about a minute to install the package, and then come on back to this section. Okay, so we're importing it as TF just so I can use the shorthand TF dot to gain access to all of my library functions, classes, etc., rather than having to type out TensorFlow. Okay, so let's first explore constant nodes. Now, first of all, what are constant nodes? They're essentially a way to store a specific constant value within a particular node, which we can then use to perform operations. We can retrieve that value, and but unfortunately, we actually can't do that much with it. It's just really a way to store that one value or multiple values in the form of an array. So we can create a node, a constant node, and store it within a variable just like we would any other Python variable. So I'm going to call this one constant node 1. And I'm just going to set this equal to tf.constant, and this will give us access to a constant node. Now, if you'll note, this little dialog window comes up and prompts us to enter a value, a dtype, which is a data type. We can enter a shape, a name, and this verify shape option, which takes in a true or false value. I'm actually only going to pass in 2 of these parameters, and only actually 1 is necessary. We just want the value, because the data type is going to be implied from that, but I'm going to enter it in anyway. So for a value, we'll start off with something simple like 1.0. Okay, so my value is 1, and if I want, I can enter a data type to be something like tf.float32, and we're going to be working a lot with float32s. The reason being that we don't need the float 64, it just takes up a little bit of extra space, and we want floats because we want access to decimal values rather than just whole numbers. Alternatively, I could actually make a constant 2, and I could do something else, let's say 2.0, and I could completely forego the data type, and this is actually a perfectly valid constant node too. So once a constant node is assigned a value, as we can see here, it maintains that value throughout the duration of the program and cannot change, hence it being a constant. Now, if we were to print out this node right now, however, we wouldn't get any value associated with it. Although a node will have been created, it will not store the value of 1 or 2 because we haven't actually created a session and run that session. So in order to actually give these constant nodes a value, we have to run the session, and that goes with any type of node. In fact, our variable nodes will require an additional step, but we'll get to those later on. So let's just print out these node values just to show you exactly what I mean. So I'll print out my constant node 1, and oops, I'm just going to copy this here print it again, and we're going to do constant node 2. So if you start a new file, as always, give this a save. Make sure when you go to run this, you select your second option here. And in this case, this is the name of my file, node types part 1. You probably won't gain access to these. These are, for some reason, popping up, even though they actually exist in a different project. So as you can see, I get 2 tensors being printed out here. There's no particular shape to these. Data type is float32, even though for the second one I didn't explicitly say so. It inferred that from the variable here. Now I could also, you can see that these constants have no value associated with them. They're just storing the value of 0 right now. Again, this is because we haven't actually run our session. So if we wanted to print out these values, we could just call something like this. We would say session equals our tf.session, so capital S. Let me just zoom in there for you guys. And we're just going to initialize it with an empty initializer. Next, we'll say session.run. Okay, and then we want to feed in the values that we want. In this case, I'm actually going to create an array, or a tensor, as I should use the correct terminology, and I'm just going to feed in my constant node 1 and my constant node 2. At the end, I'm not going to print out these 2 nodes anymore, because that's going to return me the same value as before, but instead I'm going to print out the results of the session run, which will return a value, which we could then store in a variable and print that, or we could just print these results directly. So if I go to run this, it'll give me a bunch of warnings. You know what, don't worry about these warnings. They are just that. They're not actually errors, and it's just saying that this could go faster if we weren't working through PyCharm, essentially. But PyCharm is a nice IDE to work with, so we're going to continue to do so. If you really want to suppress these warnings, I'll show you how to do that. I'll add some code at the very end that will help suppress these. Otherwise, if we look at the actual values that were printed out, as you can see, we get this tensor of 1 and 2, and that's because our first node had the value of 1, and our second had the value of 2. Now similarly, if we had run each of these individually, so let's get these out of the brackets here, and I'm just going to run one at a time, so copy this and paste it. This time we'll do 2. Then as you can see, we'll get 1 and 2 being printed out one on top of the other, just like this. Now right now we're storing single values. We can actually store a tensor, so we could have, for example, constant node 3 be a tf.constant, and we can enter in some kind of array here. I could do something like 3.0, 4.0, and I can even do another one, 5.0, if I really wanted. Then if I were to print out the value of my constant node after, of course, I run it, then it's going to print out this tensor here. Now, where possible, we should probably specify a data type, so I'm just going to go ahead and add that to each of these. They're all going to be float32s. So we can actually just copy that and paste it right in there. So when I set the type to be float32, that implies that every single one of these values within the tensor here will be a float32 also. Now the reason we got nothing printed out before is because, again, we haven't run these nodes, and so none of the values stored at these nodes is going to be evaluated. It's only once we call on the session and run that particular node that the value at that node is evaluated. So this goes for anything. This goes for even nodes that feed into other nodes. If none of the nodes are running, then we're not going to get any values printed out because none of the nodes will be evaluated. However, if we have a node, for example, one of these operator nodes, whose value depends on other nodes, and then we run that operator node, then essentially it's going to run all of the other connected nodes as well. Or at least the ones that feed into it, not necessarily the ones that it feeds into. So for example, let me just create a couple of operator nodes. So we'll start off with a basic addition one, and we store these in any other variable just like we would these constant nodes. It's just instead of calling tf.constant, we can call something like this. I'm going to call this add a node 1, and it's going to be tf.add. Okay, note that this is one of the operations. Just like if we were to do something like tf.multiply and so on and so forth. In this case, I'm just going to do a tf.add, and we're simply going to enter 2 nodes that we want to add. In this case, I'll just do constant 1 and constant 2. So if I were to run now my add a node instead, so I'm just going to get rid of this second print statement, and now instead of running constant node 1, we'll run our add a node 1. So let's just zoom out and give this a run. We should get the results of the addition. Let's just wait for that being printed, and we do 3.0. Additionally, we actually don't have to create or use a special type of node. We could do something like this. Add a node 1 equals just something like constant node 1 plus constant node 2. And then if we were to run this, we would achieve pretty much exactly the same effect as before. You know what, I'll store the results in something different just so that we can see that contrast. So if we were to run again, should be exactly the same. Again, 3.0 being printed out. Now let's say, for example, that we had another operation being performed. So let's say we want to multiply something this time. So we can either create a separate tf.multiply node, or we can simply call on the operation one of these nodes times one of the others. I'll just keep things simple. I'm going to call this mult node 1, so multiply node 1. And we're just going to set this equal to the results of adder 2 multiplied by every element within this tensor here. So we can just call on something like adder node 2 times constant node 3. So what this will do, if you understand any kind of matrix multiplication, is it will take each of these elements and it will multiply them by the results of this addition. So that's going to return us 3 times 3, so it should be 9, 12, and 15 if we were to run multi-node 1. Okay, so let's just zoom out, we'll give this a run. Let's see, we do get that, 9, 12, and 15 printed, exactly what we should expect. But this is run on multi-node 1, which means that it's not only running multi-node 1, it has to run our adder node 2, and it has to run constant node 3. And now adder node 2 itself has to run constant node 1 and constant node 2. So essentially, we get 1, 2, 3, 4, 5 nodes being run total. However, if we were to run, in this case, adder node 2, but not multi-node 1, then this is not going to perform this operation, so multi-node 1 is just not going to be run at all. It will only run adder node 2, and then that will in turn run constant node 1 and 2. Okay, so pretty straightforward stuff here. We can also deal with two tensors if we want. So if I wanted to create a constant node 4 that had itself a tensor and then perform some operations there, for example, adding each of the elements together, or adding one of these to each of these elements or something like that, that's a perfectly valid operation to perform as well. So even the results of an operation like this will be stored within a node itself. So we're essentially building up our graph piece by piece by including all of these operations and these constant nodes. Now, constant nodes are obviously very inflexible in that they can only ever hold the one value or multiple values, and that value can't change, which means they're not particularly good for use in the computer sense of trying to change variable values, or for input values. Because of course we want to be able to at some point take in input from the user, or have the computer multiply these values to predict a model successfully. So use these constant nodes whenever you want, well, a constant. The operation nodes, however, will continue to be used throughout very often, but if we want something a little more flexible to work with, we're going to have to introduce either placeholder or variable nodes. So let's take a look first at placeholder nodes, and then we'll move on. I think we'll do separate sections for the two. So in the section coming up, we'll take a look at placeholders, and in the section afterwards, we can take a look at variable nodes. Then once we've finished with variable nodes, then we can start to actually build up our model, beginning with the basic intro to the linear regression model we're going to be using. So unless you're totally 100% comfortable with this stuff, play around with it a little bit, and once you are ready to move on to the next section in which we'll introduce the placeholder node. Hi everyone, having covered 2 out of 4 of our simple node types so far, we can now move on to the third, which is going to be our placeholder node. So whereas with the constant nodes and actually the operation nodes as well, we're kind of assigning a value right away, placeholder nodes actually contain no current value when we create them. It's only when we go to run the session and therefore run the nodes that we pass in some kind of a value to these nodes. So essentially, when we build our graph up, we are saying, okay, here is an empty node that will contain a value, but we just don't know what that value is going to be right now. So then when we go to run the entire graph, then we need to pass in a value for each of these placeholder nodes if we want something to actually happen with it. So we can kind of think about these as being nodes that would take in the input into our model. So thinking quickly back to our linear regression model, y equals mx plus b, well, m and b are going to be the variable nodes. Those are things that the model tries to optimize itself, but x would be a good place for a placeholder node because we need to pass in x values when we run the program. Similarly, when we're testing the program, or training it rather, we'll probably want to pass in some y values as well, so y would be another place where we might add a placeholder node. But enough talking, you guys came here to code, so let's get to coding. The first thing we'll need to do is, of course, import TensorFlow as TF, and the reason that has to happen is because I'm starting a new file. This one I've called node types part 2, whereas previously we would work in part 1. I've actually included part 1 here. Just kind of close it up and start a new file, which also means when I go to run this guy, I'm going to have to run, of course, my node types part 2 and make sure I'm in this file here. So nothing should really occur. We should have an empty run screen because I haven't told this guy to print anything yet. Okay, once you install TensorFlow once, it should be forever installed in PyCharm unless you go and deliberately delete it. So you shouldn't have to install it yet again. Just make sure you import it here. Okay, so we set up placeholder nodes kind of similarly to how we'd set up a constant node, except that we don't provide a value right away. We do store them in variables, however. So I'm going to call this placeholder 1. placeholder node 1, placeholder 1, it doesn't matter. And we're going to set this equal to tf dot placeholder. Okay, note that takes in a few parameters, so dtype, shape, and name. There's no value parameter here, which makes sense. We don't want to pass in a value right away. Now, actually, all I'm going to give this guy right now is going to be a dtype, so dtype equals tf.float32 as usual. And I'm not going to worry about the shape or anything. Actually, you know what? I probably should have explained shapes in the previous section. I might as well get into this now. So when we talk about the shape of a tensor, and that's what I was referring to, we talk about basically the degree of the array, or how many arrays there are within that particular array. So consider this literal and primitive number 5.0. Well, this has a shape of 0, or the shape doesn't exist, okay? And this is because, first of all, this isn't in a tensor, and second of all, there are no tensors within tensors, all right? However, if I were to put this in a tensor like this, suddenly my shape takes on this value, so this would be 0, 0. My shape now equals something like 1, 0, okay? This is because there is 1, actually, you know, rather than 0, 0, these actually are just blank and blank because the shape doesn't really apply here. Well, in this case, this is actually just going to be 1 and blank because there is one member within this array, within this tensor, but there are no additional arrays, there are no tensors to take on additional shapes. If we went one step further and had something like this, an array within an array, 5.0 like this, then our shape all of a sudden becomes 1 and 1. The reason being there is one array within our outer array, and there is one member within that array, hence one outer or one inner array and one member within that array. So we could then add some variations here if we had a couple of arrays perhaps, each with just one member here, so 5.0 and then like 1.0 or something. Well, in this case, my shape is 2 and 1 because two inner arrays, each with only one member. And so if each of these had a couple of members as well, so 4.0, this one could maybe be 2.0, then in this case my shape becomes 2, 2 because again, two inner arrays, each with two members this time, and so on and so forth. So this is the basics of our tensor shapes, and that's just what it means, but it's clearly something that we don't have to specify, seeing as we're able to assign this variable, no problem. And just for the sake of demonstration, I'm actually going to add in a placeholder 2, which is also going to be a float32. Now, if I were to print these right now, haven't created a session yet, so we would get basically just some empty tensors. But if I were to create a session, so same as before, we're just going to say session equals tf.session. It's a good idea actually to keep typing this out just so you get in the habit and it becomes second nature, you don't have to think about it. Then we could say session.run, and we're actually going to print the results. So let's just go to the end, and let's say I were to print my placeholder 1. Well, rather than just entering in placeholder 1, like we would have done with the constants, we have to provide a value to this as well. So not only am I going to run placeholder 1, but I'm going to provide some values too. So I have to enter the colon here, and then afterwards provide some values. I could enter just a single value like this, or I could enter a tensor with a few values. So let's just mix things up. Let's enter a tensor, 2.0. We could do, why not 3.0 as well. This is giving me an error right now because we need to place these in curly braces, like this. Okay, so if we were to go ahead and run this now, we're printing out the results, so let's give it a whirl, and let's see what gets outputted here. And we're getting a massive amount of errors. Oh, I think I see what the issue is. Forgot to add in placeholder 1 here. I need to pass in the values there when I go to run it. So there we go, that fixed the issue. We need to make sure we're running the node itself, and then we're entering some values for it. So that's what it was. As you can see, getting the array 1, 2, and 3 being printed out there. So we would do exactly the same thing for placeholder 2, and we'd do exactly the same thing if we wanted to enter in only a single value. So for example, 4.0, going to run that again, we just get the value of 4 printed there. So essentially what this does is it assigns to placeholder 1 this particular value, or values if we entered a tensor, and then it's going to run placeholder 1 with that particular value. Now, if we ran something like placeholder 1 with placeholder 2 containing this value, well, that's not going to be particularly useful to us, as as you can see, it gives us this massive error because it's saying, well, placeholder 1 still doesn't have a value. We haven't assigned it here. So make sure any time you're going to run a placeholder node, you need to provide a value for that. So it's important to keep track of all of your placeholders, as if you don't enter in values, you get this ugly error here. But that being said, we can actually perform some operations on placeholders. So we're going to take this one step further and create an operator node. So we'll just do a simple multiply operation, okay? We'll call this multiply node. And this is basically going to be the result of placeholder 1 times placeholder 2. There we go. Now what I want to do is run multiply node. So I'm going to replace the node I'm going to run with multiply node. And now I need to enter values not just for placeholder 1, but also for placeholder 2, because I'm going to be using both of these placeholders. If for whatever reason I was only using one of these placeholders, then I'd only need to enter the values for that. So actually, before we do this, let's just do, we'll call this multiply node 2. And we're going to run multiply node 1, which I'm just going to create right now. Whoops, didn't want it there, I wanted it here. This is just going to be something like placeholder 1 times 3, okay? And so if we wanted to run just multiply node 1, as you can see, we're taking in a literal value and we're taking a placeholder node, so we need to provide a value for placeholder node. This will suffice, 4.0. So let's go ahead and give this a run, and let's see what output we get. We get 12. So that's to be expected, as 3 times 4 does in fact equal 12. But if we were to run multiply node 2, we need to provide values for both placeholders 1 and 2. So let's run that. And now we need to provide a value here. And we need to provide a value for placeholder 2. So in this case, let's actually switch it up. Let's make this a tensor. We'll do 2.0, 2.0, and let's do 5.0. Okay, doesn't really matter. It's entirely up to us. So now if we go to run this, we should get our tensor here being multiplied appropriately. We are multiplying each of these by 4, so of course 2 times 4 is 8, 5 times 4 is 20, so we know this is working exactly as it should. Okay, so let's just zoom out and review what we've done so far. So that's actually the basics of placeholders. Are very straightforward. You just need to make sure that you are providing a value for them if you're going to use them at some point down the line. Even if there's a node connecting a node, connecting a node, connecting a node that connects to a placeholder at some point, because it's still connected to that placeholder, you do need to provide a value at some point. However, if you're not going to be using that placeholder like we saw in the first case with placeholder 2, you don't need to provide a value for it. It just doesn't make sense to do so. But as you can see, when we run this, we are entering in values, so it's a very good place to enter an input. We can kind of think about them as being like function parameters. Alright, so placeholders, good place for input. They are just a promise to hold some kind of value. Once they are assigned a value, we can treat them just like we would a constant node. So with that being said, we can conclude this part. Let's give this a save, and we'll end this section moving on to the next part, which is going to be our variable nodes. Now, these are going to be kind of similar to constant nodes, but obviously they can change, hence the name variable. And there's actually going to be one extra step we need to take if we want to run them. I'll explain that later. Otherwise, make sure you're comfortable with placeholder nodes before moving on, as things are only going to get weirder from here on out. So let's go learn about some variable nodes. Alright guys, having explored 3 out of our 4 basic node types, we can now move on to the 4th and final one, which will be our variable nodes. So variable nodes initially start out like constant nodes in that we typically assign an initial value, maybe a data type, but there's actually some pretty significant differences between variables and constant nodes. So the 3 main differences are the fact that although we store an initial value, we can later change that value in a variable node, whereas with a constant node we actually can't reassign any kind of value once a value is stored. The second big difference is that when we go to run a variable node to evaluate the value it holds, we have to call upon an initializer to first assign the value to all variables. We'll explore this process towards the end, and the third difference is going to be the fact that our variable nodes actually have a ton of attached extra functionality. So this means there's a bunch of extra functions that we can call on variable nodes, there's a bunch of different values we can retrieve that aren't necessarily there for our constant nodes. So let's jump right into some examples. I've just started a new file, as you can see, node types part 3 this time. So when I go to run things, I need to make sure that I'm running my correct file. In this case, node types part 3, empty screen, that's what I expect. So the first step is always going to be to import TensorFlow if we want access to any of the TensorFlow stuff. So we're going to call import TensorFlow as TF, and now we can start by creating some variable nodes. So I'll start with just the one for now, variable node 1, and I'm going to set this equal to TF dot variable, capital V, because this is a class, or, well, we're actually creating an instance of the class. And if we open up our brackets here, you'll note there's a ton of different parameters we can enter in. So already you can see that our variables are quite a bit more complex than our constant nodes, as a constant node only had a few options to choose from. Well, because we're keeping things simple, I'm just going to pass in a simple value of like 5.0 or something, and I might as well pass in a data type just to make things as clear as I can. tf.float32 should do the trick. And for demonstration purposes, I'm actually going to create a constant node as well. tf.constant, this should be pretty routine to you guys by now. I'll just fill in a value of 10, I can add in a data type as well if I really want. tf.float32 again, And that's really all there is to setting up a basic variable node. So like I said, it starts out looking very similar to a constant. The big difference that we see right off the bat is when we go to run these nodes. So whereas I could just create a session and set this equal to tf.session, capital S again, and then go ahead and run this one. So I could print session.run, and I could enter in my constant node 1. I can absolutely do this. So if I go to run this one, it's just going to print out the value found at my constant node 10.0. I cannot actually do this with my variable node. So if I replace my constant node with a variable node, oops, and try to run this, then it's going to give me a bunch of errors, okay? The problem here is that although we think we've assigned the value to this variable, we haven't actually initialized it. So as of now, this variable node 1 actually doesn't hold this value, and that's why it's throwing so many errors. In order to have this take on a value, we have to create a global initializer. So let's call this init, and this is just going to be our tf.global variables initializer. And then we have to run our initializer. So actually, you know what? I'm going to print this on this line underneath, and then we're going to call on our session.run, our initializer, and then we can run our print statement. So now if we were to run this, we should successfully get the value of our variable node printed out, and indeed we do. That's just going to be 5.0. Now this global variables initializer here, this initializes all of our tf.variable nodes. So this means if I had, say, node 2 and 3 and 4 and 5, I had a bunch of different variable nodes, this call to our global variables initializer just once will initialize all of them, okay? So typically we'll only ever have to call this once before we go to evaluate any values found at those nodes. Now again, if there's going to be any other nodes that rely on our variable node to have a value, so those are connected nodes leading into there, then we have to call on our global variables initializer before we gain access to any of the values that have to do with our variable node. So if you have any variable nodes at all in your project, always make sure you're calling on this initializer. Now we don't actually have to create a new variable. I could just have passed this line of code into my run statement here, but just trying to make things a little clearer for you guys. Now, other than that, seeing as we've initialized our variable here, then we can use it just like we would any other kind of node. So for example, I can perform any kind of operation on here. I can multiply this by constant node 1 and run it. Should give me 50. Indeed it does. 10 times 5 is 50. And I can perform a large number of other operations on these guys. So right off the bat, when I start typing out my, let's say, constant node 1 dot, note that there's really not a lot I can choose from, okay? However, if I call upon my variable node dot, then there's a ton of different functions and values that I can retrieve. Okay, and the fact of the matter probably stems from our variable being a class, whereas constant is just not a class. You can tell that both from the capital letter here and from the fact that if I call variable, let's say if I call tf.variable, it is a class here, whereas tf.constant does not provide us a class, it's just a function. So something we might want to do with variable nodes, because, you know, otherwise why not use just a simple constant node, is going to be to reassign the value. Now, all I need to do really is call upon my variable node 1 dot assign, and then enter in a new value. In this case, maybe I want to enter in the value of 10. Now, doing this itself is not quite enough. We have to actually run this just like we would run something like this to evaluate the node or run our initializer. So if I were to assign the value of 10 and then run it like this, well, nothing's going to happen. In fact, let me demonstrate that. So let me just print our session.run, and I'm just going to print out the new value of variable node 1, or so I might think. So if I go to run this, but I get 5 printed out there, so clearly this reassignment hasn't worked. Well, like I said before, we're going to have to run this in our session, just like we would have done otherwise. And now it can take on the value of 10, so if we go to run it again, it's going to print out our 50, and then it's printing out 10, because we've successfully reassigned its value down there. Other than that, that is pretty much the basics of our variable type nodes. Now, like I said, there's a ton of different stuff we can do with them, so I suggest playing around with it a little bit before moving on to the next part. But at this point, you know actually everything you need to know about our 4 basic node types to start taking a look at our linear regression model. Now, I know we haven't covered each of these in huge depth. I could go much deeper into each of the topics. I just wanted to get you guys knowledgeable enough that you can start working on the actual linear regression model and get into some interesting stuff. Because that's what we're going to be covering in the next couple of sections, and that's really what I've been leading up towards. I just wanted to get us familiar enough that we can successfully build up this model and get started with some real machine learning. So I think in the next section, before we actually start building up the model, which we'll do over the next few sections, we're just going to start talking a little bit more about linear regression itself, how it's going to work, and kind of go through the steps. Then we'll start actually writing the code. So once you're comfortable enough with variables, given them a little bit of practice, and are ready to move on, do so, and we'll see you in the linear regression sections. Hi guys, by this point we've learned some of the key components to building our computational graph. Specifically, we covered 4 different kinds of nodes we're going to be using throughout, as well as how to create a session and then run it to evaluate how those nodes' values will change. So with that in mind, we know just about enough to start building up our actual computational model from the ground up. Before we start writing any code that represents a model itself, however, I'm just going to take a few minutes to talk a little bit about linear regression, which is going to be the model that we'll be using, as well as give a brief overview as to the steps that we're going to be taking to build this model in TensorFlow. So for those of you who are very familiar with linear regression, particularly using it in TensorFlow, then feel free to skip this section. If you guys know nothing about linear regression or know some but not how to use it in TensorFlow, then this might be a good place to start. Okay, so I'll try and keep it short and to the point. Now, first of all, why linear regression as opposed to any other machine learning model? Well, in my opinion, I think linear regression is probably one of the simplest machine learning models to simulate. And this is because it operates on the principal equation of a line, which is just y equals mx plus b. So typically, once our model already works just fine, it will have adjusted m and b to provide some optimal values. We'll simply be able to enter in some x inputs, and it will output where the y values should be, based on this line that will have been optimized by our program. And essentially this is a really good way to predict where points should lie on a line of best fit. So essentially we'll have a bunch of data points and we're trying to find a line of best fit through those points. We'll use our model to optimize m and b until it finds that perfect line, or as close to perfect as we can get. And once it finds that good line, then we'll have a complete model there. So as I said, our program will try to adjust m and b until it minimizes what we call loss. Now, loss is the difference between an actual y value and the y value that a line would predict. So let's say we have some arbitrary line running through a set of data. Well, the loss will be basically the sum of all the differences between the actual y points we get and the y points that run along the line itself. So by minimizing this overall loss value, we're actually computing the line that best fits the data, as a minimal loss will basically imply that the points are as close to the line as they can get. Now, if you want to learn more about the specifics about how linear regression works, I do recommend that you do some research of your own. Otherwise, I'll assume that you get the basic idea, and we're going to cover some of this stuff again anyway once we start writing the code. So we're going to go about doing this by first building our model and then training it. So we'll build the model up using a series of nodes. Some of them will be placeholders, some of them will be variables, some constants. And we'll probably start with something like some placeholder nodes for our x and y values, as we want to take these both in as inputs. At the end of the model, we'll be able to just take in the x values as inputs and have y values as outputs. But at least in the training phase, we want some x values and their expected y values, so the y values that correspond with them, in order to train our model at least. Then we'll probably have some variable nodes to represent m and b. We'll just start out with some initial guesses and see how good or bad those guesses are by measuring our loss. Then essentially we'll create other nodes, and finally we'll run our program in the training phase, and our program will basically adjust m and b values to overall minimize the loss based on some kind of inputs that we enter. So after it's been sufficiently trained and has found optimal values for m and b, we'll again be able to just enter in any kind of x value, and it should give us roughly what the corresponding y value should be. Okay, and our final model will just provide a good fit line through our data and should be able to predict those y values. So the underlying concepts here are fairly simple, but just given the fact that this might be an entirely new thing to you, TensorFlow and rank machine learning programs, it can be a somewhat complex process and is easy to get lost. So hopefully you guys understood some of this. If you want to learn more about linear regression, again, I encourage you to do some research on your own. Otherwise, I'll try and go slowly through the actual building of the computational model and explain exactly what's going on at each step so that we're never lost. But as always, and it's very important here, you need to understand the stuff that we are covering in the current section as well as have covered in the previous sections before moving on to the next, because like I said, it is very easy to get lost along the way if there's like a couple of lines of code that don't really make sense right away. Otherwise, with this brief intro done, we are just about ready to start building up our computational model. As always, we'll start by building the graph, then we'll start by and then we'll move on to train it, and finally we'll use some test data to assess the accuracy of our model. And we're going to do so in 1 or 2 different files. So this one I just created a new text file for. I guess I'll include this in the final product. Although again, hopefully by the end you won't need this, as you'll be fairly familiar with the mechanisms. So let's go ahead and get started by building up our computational graph.